Now we will look at the angular momentum of a rotating rigid object. Let's say that we have a disk as an example for a rigid object that is rotating about an axis that is perpendicular to its center, so it's along the z-axis, that is the rotation axis. And if I consider that this object is made up of particles, as we normally do, the rigid object is made up of particles. Mass of each particle is m sub I. The position vector is r sub I. So this particle is at a distance r sub I from the origin, and it has mass m sub I and tangential velocity v sub I. Now we know that for circular motion, v sub I is equal to r sub I times the angular speed omega. This angular speed omega will be the same for all particles that make up this object. So if I pick another particle here, it would have the same angular speed. So if I calculate the angular momentum of this ith particle using r cross with mv, so it's ri cross with mvi, this would be equal to mvi ri in k hat direction. So if you use the right hand rule, r cross with v is in k hat direction. And because I can write vi as ri times omega, so this would be equal to m ri squared omega in k hat direction. So if I want to calculate the total angular momentum of this rotating rigid object, total angular momentum, I would add up the contribution from each particle so that I would get total angular momentum, and it's in the z direction, is sum over I Li. It will be sum over I mi ri square times omega. Now in parentheses I have what I know to be moment of inertia, so it's I times omega. Therefore, I find that the angular momentum, the total angular momentum, is I omega. So it's the moment of inertia times the angular speed. And I find that this angular momentum, total angular momentum, is parallel to the angular speed, angular velocity omega here. So it's a vector, it's pointing in k hat direction using the right hand rule. And why is that? Because this is the sense of rotation, and that is counterclockwise. So if I take a derivative of this angular momentum with respect to time, rate of change of angular momentum, I get I d omega dt, that is I alpha, and I alpha we have shown previously to be equal to the net torque that is applied on this object. So it is dl dt is equal to the net torque. So as we have shown previously, if the net external torque acting on this object is 0, that means dl total dt is 0, then the angular momentum must be a conserved quantity. Initial angular momentum vector should be equal to the final angular momentum vector. So this is the case. Angular momentum can be conserved only if this condition is satisfied. So if that is satisfied, then I have the total angular momentum constant of this motion. Now let's state this. If the net torque acting on a system is 0, then the total angular momentum is constant in time. And since I have shown that the angular momentum for a rotating rigid object is equal to I omega, so for a rigid object, this would imply Lz is a constant, which means I omega product is a constant. I initial omega initial equals to I final omega final. Now you may be wondering, how can I have the moment of inertia of an object changing? Well, the moment of inertia of an object can be changed by causing a redistribution of mass. So I can be changed by mass redistribution. A very good example of this is given in ice skating. For example, ice skater, and I have added a link to a YouTube video at the description of this